Hi there, and welcome to a little bit of information on how I'm going about designing my truss for the BCIT Technology Teacher Education 44 Laser Cut Challenge in the year 2022. Now, before I get there, I'm just going to have to clear a few things off my desk. I've got some really cool 3D printed gears that I've been playing around with for perhaps an upcoming project, and you can see these ones just so cool. You can get double helix in there. That would be really tough to machine, but that might be down the road in this course. What we want to do today is we want to take a look at our truss designs. And keep in mind, I'm going to show you 3 different design sketches that I've come up with here, but there are many, many different types of truss. There's just Google types of truss, and you're going to come up with a whole bunch of different options for making your design. But okay, let's take a look at one way to go about doing our work right here. And the first thing I'm going to get you to do as part of your assignment is to come up with 3 different design sketches. There's so many different ways to build a truss. Now, for our particular design challenge, there's going to be some very specific things that you have to design your truss to do. For instance, everybody is going to have the same load criteria. And so there's going to be a distance of 400 millimeters right here on the long side of the truss to where the load is being applied coming down right here, and 150 millimeters on this side of the truss. So when you're creating your sketch, probably a great way to start is just to take a little ruler and lay it down and give yourself 4 centimeters and 1.5 centimeters, 40 millimeters and 15 millimeters, and draw it at a 1 to 10 scale and start putting different things in and figuring out a rough idea of what you might like your truss to look like. So here's a few different ideas that I'm thinking of, and I'll probably show you one in class like this that I call the bicycle spokes. And thing I like about this is that all of these members in here are going to be loaded in tension because the force is pulling down right here. We've only got one point load, which is different from West Point Bridge Designer where you had a truck driving across multiple nodes on here. So you needed to have equal strength across the truss. And that allows us to sort of cheat and move the thickest part of the truss over top of where that point load is going to be. So that's not cheating, it's just good design, but it's part of the solution that if your thick point of your truss is over here and your load's over here, you're doing something, well, maybe brilliant, but probably not. So anyways, these ones are all loaded in tension coming down right here. That means, of course, the members coming along the top are going to be in compression. Because our load is much closer to this support node right here, this is going to be exerting a much greater upwards force than this one over here. In fact, all of our reaction forces will be the same, and I'll go through and calculate those with you in a moment. And anyway, this is one possible design I might go with. I might develop it a little bit more. There's the good old Warren truss. I think this is one that people had a lot of success with in the West Point Bridge Designer Challenge. And so go with what you know type of thing. And today I'm going to do some more analysis around this one. And then, like I say, there's many, many different types of solution. This is kind of based on the idea of a scissors truss, where since you know the top members are going to be loaded in compression, why not make them into a truss? Because trusses are good at dealing with compression. Now, do keep in mind all the rules of the challenge, one of which is that each of your nodes has to be at least 70 millimeters apart from any other node on that plane. Okay, so keep those nodes separate by 70 millimeters in order to have a legal truss. All right, so here's a few different designs, and I'm going to take a look at this Warren truss, and I'm going to do a few things to figure out where my forces are going to be, what my reaction forces are going to be, and how strong can I make this using some fairly simple measurements and straightforward calculations. We can take a look at it on the computer. I'm just going to go through some hand calculations first. Thankfully, I've got them all done. Now, one of the things, of course, that you can do pretty easily is you can say, well, how tall do I want my truss to be? And you can say, I want my truss to be 200 millimeters tall, and use that as your starting point. And then you can calculate the different side lengths. that works fine. You can say that, you know, that whatever criteria you want, you can come in and say, I want my truss to hold 400 newtons, and then start building your truss based around something like that. You may find that you're able to get it to that. You may find that you need to change your scale a little bit, but you can start working through it. And certainly when I show you how to use the computer to do this a little later on, it goes fairly quick. What I said was, well, the shortest member you're allowed to use is 70 millimeters. And so I said, well, if I've got 3 members right here to keep this nice and simple, and I'm going to connect them coming down right in here, because with this being a 150 millimeter gap and you needing to keep your nodes 75 millimeters apart, the only way you can get a node in right here is to have it 75 millimeters from each space, because you couldn't fit a second node in there. So ultimately I might have that come down right there and that come right up there. I'm going to have to check right in here to make sure that that dimension gives me 70 millimeters, but I'll worry about that when I take it over to AutoCAD. I don't feel like doing the math on that right now. I'm going to come through here and I say, well, if I've got 70, 70, and 70, that means that this side of my truss is going to be 210 millimeters right along here. And based on that, a little bit of Pythagoras, I can tell you that the height right here is going to be 147. Okay, that's the 210 squared minus 150 squared, and take the square root of that. It's almost the same length as right here. Pretty close. I know the height right here now. I know this is 400. And so I can do a little bit of Pythagoras, and I can say I'm going to be 426 millimeters long on that side in order for them to meet up. Now, that gives me some of the overall geometry of the truss. You can figure it out mathematically. You can draw it to scale. Get actually a compass works great for doing all this, or a divider, and your ruler you can get in here and you can lay all this out and measure it out. This is drawn 1/5 scale right in here. Okay, so now this is where you need some of the data from our compressive testing lab, because I've said, well, if I'm going to put 3 members right in here and I want them to be as strong as possible, and they're each 70 millimeters long, what's the compressive load that a 70 millimeter member can handle before it fails? Well, the thickest member that the thickness of the board is already set. You're using 3 millimeter MDF, and it's pretty accurate to 3 millimeters. Not perfect, but pretty good. So the thickest piece that you're going to get is 3 millimeters. Well, how wide can you make that? The widest that you can go according to the rules is 7 millimeters. So if you've got a 3 millimeter by 7 millimeter cross section by 70 millimeters long, you can take that piece, put it on the compression testing jig, and get a value for it. I haven't done that. I don't have a number. This is the great thing about being the teacher. I can pull random numbers out of the air and make it happen. Or maybe I have done that test and I know it and I'm just not sharing it with you. But I'll guess that it's 200 newtons. I wouldn't use that value for your calculations. I'd go to the lab and test it. But anyways, let's say 200 newtons for a 3 millimeter by 7 millimeter by 70 millimeter long piece of hardboard, so that I can start doing some calculations here. Now, since the edges of the truss are nice and straight in here, we can actually simplify this truss a lot and say, well, all of my vertical force is coming straight down here. All of my, the rest of it's coming down on this side. All my vertical force from the reaction point right here is coming up this way, is a better way to say that. All of my vertical force from this reaction point is coming up through there. And what we've got in the middle right here are just zero force members. They're not actually carrying a lot of load, because they're just there to keep this member from buckling out to the side in this direction. They're there because you've got to hold the nodes in place, because remember, nodes are pinned, and if you don't fix that node in place with a triangle, it's going to pop out to the side. Okay, so I'm ignoring these ones in the middle for right now, and because I know that they're straight. If they came out like this, okay, that would make for a more complex calculation, and I'd probably head right over to the computer to start figuring it out right on there. Could be done by hand, but it would be faster on the computer. This one, I think I can do it faster by hand like this. Okay, so now I can take a look at here and I can say, well, if I've got if I've got 200 newtons in each of these members before they buckle, and I know the geometry, I can say, well, 200 newtons acting in the 210 millimeter direction, okay, gives me the proportions for the rest of the triangle because I've got a 150 millimeter direction and a 147 millimeter direction. So 200 to 210 is the same as my horizontal force in the 150 dimension or my vertical force in the 147. And if I work all that out and do those ratios, I've got 200 on the side. Okay, that's the sum force, that's the total magnitude of the force, with two components making that up, 140 newtons lifting up on this node at the top, and 143 newtons pushing out on that node at the bottom. There's also 143 newtons pushing over that way and 140 newtons down. Every action has an equal and opposite reaction. So what's going to be the total load that this truss can support? Well, if I've got 140 newtons pushing up at this end right here, and this is a little flat diagram of my truss. I've scaled it down back to 1/10 right here. I've got 400 millimeters here. Another 150 millimeters right here gives me a total length of 550 millimeters for the truss. My force is acting right here. My reaction force is out here. My 140 newtons times the 550 meter lever arm that it's acting at, okay, is got to be counteracted by this force in here acting on a shorter lever arm. So if the moments are the same, this has to be the greater force. And I say that I'm going to have a 192.5 Newton total load acting down at this point. And therefore the force acting in the vertical direction at the other end of the truss down here, okay, is going to be 192 newtons minus 140 newtons is going to give me 52.5 newtons acting up as my other reaction force right in there. Okay, so that's pretty much a simple moment problem. We've solved that before. And really, I don't care what you do for the rest of your truss in here. We're all getting 52.5 newtons at that end and 140 newton. Well, the ratio is going to be the same. Your total load is going to change, but they'll always be in the same ratio because the spacing between these two is always the same. All right, so we've got some geometry laid out there. We've got some numbers laid out there. We can slap this down into a diagram about right here. And since I've got 52.5 newtons acting up this way, and that is in the 147 millimeter direction, so that's acting in the vertical direction, my 52.5 is to 147 as the force of over here in the left members running up and down right there is in 426 because we calculated that 426 millimeters earlier, and our horizontal force is to 400 millimeters. Calculate this through, and this tells me that I've got 152 newtons in compression right up here, and 143 newtons in tension pulling this way. And that last calculation might seem a little bit redundant, but it's really good to do it because it allows you to double check and say, well, if I've got this one pushing out at 143 this way, I can go back and check and say, yes, in my previous calculation I said I had 143 pulling out that way. Let's just double check. There's that 143 showing up right in there, going out to one side. And very important, I've got 143 going that way, 143 going that way. So my bottom is 143 in tension. And I'm not going to panic too much about the tensile forces right now because tensile forces are fairly easy to deal with in these structures. They don't take a lot of weight because you don't have to fight buckling when something's in tension. It's when you start loading them up in compression that you've got some issues. And so up here, I've got 152 newtons in compression. And on this side, I've got 200 newtons in compression. And of course, spaced across some members. I want to know how many nodes I have to put in on this side, though, in order to make this a good functioning truss. So I want to keep my weight fairly efficient. I don't want to make my members any thicker than I need to, and I don't want to have any more nodes than I absolutely need to. So I went back and I said, well, my starting figure was, I said, a 3 millimeter by 7 millimeter by 70 millimeter long member holds 200 newtons. Again, that figure might be complete baloney. but I'm using it for my calculations. So how long can it be to hold 152 newtons? Now, when we talk about column buckling, and we assume this is failing in buckling, okay, Euler buckling to be specific. If it's not failing in Euler buckling, you're going to get some different numbers in here. So you might want to go back and do a test to double check this, because we are getting very close to having our slenderness ratio down around 100 when we start talking about the 70 millimeter long, 7 millimeter members. So anyways, let's assume Euler buckling. It's a squared relationship. So if I compare the two loads that I want, okay, I can say that the 200 newtons that I know compared to the 152 newtons, so I do that division, take the square root of that, that I can have the longer node over on this side carrying less force be 15% longer, 1.15 times as long as the ones on this side. So that gives me 70 millimeters that I had on this side times 1.15 means that I could have nodes on this side go up to 80.3 millimeters long, and they would fail at the same time as the 70 millimeter long ones would fail on this side. So that would be very efficient to be able to space these all 80 millimeters apart coming down here. However, how many do I need to space them 80 millimeter apart? Well, that gives me 5.3 nodes. Now, I could go with just 5 nodes on this side, and or I should say 5 members on that side. And if I went down to 5 members on that side, then well, they'd be just a little too long, and this side would probably fail first. This side might be a bit too stronger, which would be okay. It could mean that instead of using 7 millimeter members on this side, I'd use the 7 millimeter members on this side and like 6.3 or something like that on this side, saving a little bit of weight from the structure. However, I could also take a look at this and say, how many nodes do I need? I could just round that up to 6 and say, I'm going to have 6 members on this side, each of them 71 millimeters long. So, yeah, you could get out here and come along here, and if I wanted 71 millimeters long, this is a 1/5 scale, so that's going to be 71 millimeters is going to be 14. I'd have one there, and then 28. I'd have one there, and what did I say? 14, 28, 42, 42, 56, and then there should be another 14 in here, somewhere in here if I did that right. There's 1, 2, 3, 4, 5, 6. I think I might have been measuring a little off, but that's where I'd have my nodes spaced on this side, coming down here, each of them 71 millimeters apart. Now, of course, that 71 millimeters is quite a bit shorter than the 80 millimeters that would make this side the same as that side. So I could take a look and I could say, well, I could make them a little bit thinner. And since a 70 millimeter member can hold 200 newtons, or whatever the real value is, and we only need to hold 152, we can take a little bit of a ratio and say this one's not squared because this is this is the B measurement, okay, not the H. If it was H, it would be a cubic measurement and really, really matter, but this is the B. So this is 152 out of 200. So 7 millimeters times 152 by 200 gives me a thickness of 5.3 millimeters. So if I make these ones over here 7 millimeters thick, these ones over here can be 5.3 millimeters thick and should fail at about the same time. Should. It gives me a starting place to go back and do some tests. You might find your data gets a little bit off, but you don't need to go and build the entire truss in order to check this out. Anyway, this has given me some geometry for my truss that I'm interested in working on. I'm going to have 3 members on this side and 6 members on this side, and it's going to have a height of 147 millimeters. Now I'm just going to set that off to the side right here, see if I can keep that open as a reference window and scale that down, tuck it right in there, and let's bring up AutoCAD. There we go. We've got AutoCAD coming up right in here. I've got my reference design over here. And let's see how I go about building this truss in AutoCAD. Now, you don't have to build this truss, but here's a few tips and technique that might help you out with designing your truss in AutoCAD. So here we've got the start point AutoCAD drawing. And I've already fixed in the 30 millimeter diameter starting nodes for you, and they're spaced the proper distances apart. So it's pretty hard to get that wrong. Now, when you come in and start drawing on here, put your drawing onto the nodes and members layer right here, and pick a dimension to start with. And I'm going to start by making a line that comes from the center of this node and comes up 147 millimeters, so at 0,147. Okay, and my next point, I'm going to come down right here. Okay, and it should snap to the center. Check down at the bottom, make sure that your object snap's turned on and that you're snapping to centers. And that'll save you a lot of work. And this is the skeleton of the truss right here. Okay, should look fairly familiar. Now, I said I wanted to break these down into equal segments. So there is a command called divide. I'm gonna break this one down into 3 segments, and you won't see anything happen right away, but you'll be able to see it in a minute. And then I'm going to say divide this one down into 6 segments. Okay, and now I'm going to create 10 millimeter diameter circles at each of them. Okay, now if you're not snapping to something right in there, come to your object snap right here. Make sure O snap is turned on. That's your F3. And then you can click on different things to click on. You do want to click to node, and I should be clicking to nodes as we go along right here. Okay, and let me do a circle. Circle, center point for a circle. There we go. I just clicked to a node right there, and I am going to make that 10 millimeters in diameter. Now remember, AutoCAD does radius unless you specifically tell it to do a diameter. So I'm just going to do 5 millimeters in radius. And I'm going to repeat that circle command. I'm going to, everywhere where I've got a node, I'm going to put it in at 5. This is exciting, isn't it? Well, that's why they've got fast forward on AutoCAD on YouTube. And 5. Okay, there's a bunch of nodes for me that I'll come along and draw some into a little bit later on. Then right along the bottom here, I said I wanted to split this in half so that I'd be able to come down right here and come right up there. So again, I can go divide, select an object to divide right there. I want to go to 2 segments, and I will go circle. There's that node, and then 5. And then this segment down here, I'm going to want to come down. That'll come down right there. So I want 1 segment 2 segments, 3 segments, 4 segments. That'll be 5 segments. Let's check and make sure that works out. Divide the side. Oh, divide. And I want 5 segments right along there. And circle. 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 Okay. Now it looks like I've got some places to put nodes down in here. And so I can come along and draw in my connecting members. And I can go line. And we might want to play with some of that geometry a little later on. We're going to pump it into a couple different analysis packages and take a look at how it comes together. All right, now these members right up here, I said I wanted them to be 7 millimeters thickness. So what I'm going to do is I'm going to come in here and I am going to offset 3.5 millimeters to that side, and this one 3.5 millimeters. Oh, don't do that. That one wasn't going to be quite as thick. So finish that. Offset 3.5, object to offset. Offset it to that side. So there's my 7 millimeter thick because I offset it on each side. And what that gives me is a perfectly aligned member coming right down through all of those pieces right there. My bottom member, I haven't calculated exactly how big I need it to be. I'm going to make it 2 millimeters because it should be loaded purely in tension. So what I'm going to do is I am going to do an offset. And I want to still set to 3. And I'm going to offset it by 1. There we go. Now keep in mind that won't be exactly 2 millimeters because there is like a 0.1 millimeter kerf on each side for the laser. And let's do this side since it's carrying the exact same force. There we go. That comes right along the bottom there. And then up here, I'm going to make this one, what did I calculate that? 5.3 millimeters wide. So that's going to be 2.7, I'll say 2.8, yeah, 2.7 millimeters on each side should give me 5.4. So 2.7 millimeters each side. 2.7. There we go. Now I still need to come back and add a little bit of thickness to these in the middle. Before I do that, I did just want to check one thing. I'm not 100% sure that these are 70 millimeters apart right in here. And if they're not, I might have to play around with some of the dimensions. These ones down here definitely aren't 70 millimeters apart. So I may have to play with a couple of these nodes right here. In fact, right down here, that one's violating the 70 millimeter node. So I am going to take that one and delete it, and that, and delete it, and that, and delete it. And I'm going to have to draw a line from there to right there in order to brace. that node right in there. Yeah, it was looking kind of ugly before anyway. Shouldn't be a big deal so long as this one's all in tension. It's really only where you've got things in compression that you want to have short lengths with lots of node bracing. And let's just check with a dimension. Oh, that's only 55 right in there. Okay, so that one's not quite going to be okay. Now we've got a couple of options. You can take this node and move it out here a little bit, which from a design point of view might not be too bad. You remember that there was a lot of arch structures that did fairly well uh, in our design challenge in West Point Bridge Designer, or you could move this one a little bit further over in this direction. Now, anytime you've got to move things around in AutoCAD, remember that there is the stretch command. And stretch works pretty neat. So if I take that one right there, that one right there, and that one right there, and I take it from the middle right there, I can move it over. Oh, I can't quite go 10 spaces. Let's try moving it 5 spaces over that way. Oh, I took too much of those ones. I'll have to redraw them later. Um, the problem is I selected the whole thing instead of just the ends. But let's take a dimension here. That's not going to do it. I'm only at 57 right now. So this one is going to have to move out this way a little bit more. We're going to have to play with that geometry just a little bit before we start making this truss into something that we want. So check your dimensions right in here. Make sure everybody is 70 millimeters apart. And this side now I'm a little bit worried about. Oh, that one's only 55 apart as well. So I might need to play around with some of these dimensions a little bit. I'm going to take a moment and fix that up. You don't need to watch all that as I play around with it. And I'll get this truss to a point where it's worth taking a look at in further detail. Works better when mute's off. um, Thought I'd mention that one of the tricks that I'm using here to make sure everything's 70 millimeters apart is that I'm just drawing a 70 millimeter diameter circle about that truss node and making sure that there's no other nodes within that range. And then I can snap to the intersection of those two lines, and that should get me the absolute minimum length truss right there. I'll come back and delete these, or minimum length member right there. I'll come back and delete these later on. So I'll keep on fixing this up, and we'll have a look when it's done. Okay, so here we go. I've got this set up now so that we've got all of our members tucked away in there. And although it's not exactly like I sketched out on paper, I probably should have been drawing it more carefully to scale when I was putting on paper, and I would have noticed that some of my members were within 70 millimeters of each other. So this is going to be the overall design of our truss. Now, before we go to laser cutter or do any more analysis on it, we can come in here and we want to start doing some trims. Oh, right. Before I do that, I've got to add some thickness to these center members. I just wanted to talk about the fact that I finally got everything legal. Okay, I just did a few more offsets in there, and I didn't think these ones in the middle were going to be carrying all that much force. If they were carrying force, it'll be these ones right here carrying force in tension, I expect. And so therefore I didn't worry about making them too big. I just made them 3 millimeters. Now, right now this is set up so that when the laser cuts, the laser will cut everywhere where there's a line. So our nodes are going to end up getting sliced to bits. And we really don't want that to happen. So what we have to do is we have to come in here and we have to do a bit of trimming and erasing. So when you come to a node like this, zoom in on it, and I'm done offsetting, and trim. Okay, and then tell it you just want to trim things right in here, and right click, and then you can come in here and you can start getting rid of all of these little bits that are coming right in here. Now you also want to get rid of these little bits. So that you've got a continuous join right. This is one of the more tedious parts about designing in AutoCAD. There are some shortcuts around that when you're designing in Fusion 360. But there we go. Now each of those is trimmed down nicely. So we can get out of the trim mode. And then you can go to erase mode. And let's get rid of all that. And of course we don't want, oh, I've still got a trim over on that side, but we'll take care of that in a minute. And we can get rid of these center lines because their only purpose was so that we could use the offset to get things spaced in there nicely. And watch out right here. Don't forget about that one little place. We got to go back and do a trim. Otherwise, the laser is going to come down and it's going to cut that right off. Now, if you want, you can also do a fillet. Okay, so we've done all of our trims. Follow the edge of that circle around. That all looks good. And we can do a fillet if you want. And you set the radius. Our maximum radius that you're allowed to do in the rules is 3 millimeters. So you can go from right here to right there, to right, repeat fillet, there to right there. Now, careful right in here because you can't fillet to this line over here. Okay, see if you fillet right there, you're breaking the rules because you're making the node bigger than it's allowed. So right in here, there we go. There's a little bit of overlap right in there. That's still probably going to be fine. Why is that circle showing up like that? That was because I over filleted it. So maybe this one only needs to be a 1 millimeter fillet. You can undo that fillet right there and set your radius down to 1.5 on this side and fillet to right there and repeat that fillet right there. And in here, we probably better do that to 1.5. These ones, I think we can get away with that. Now, filleting probably doesn't add all that much strength to your structure, but it's a general rule in structural design that if you can avoid sharp corners, that it's probably a good idea to avoid sharp corners. And we'll set the radius to 3 for the remaining ones on here. There you go. And then take a careful look at that corner and make sure that looks like something that you want to have cut out. Then go ahead and do that for each of your remaining nodes. Okay, so I've gone through and I've erased a few lines on there and got everything looking pretty good. Now, this is a point where you really do need to go over this carefully. And hopefully, if you're looking at it carefully, you can see one place where I missed a trim. Because if you miss a trim in that place, then you're going to spend 15 minutes doing your laser cutting, and you're going to find out that the laser cut it right there, and you've got to go back and cut it all over again, and you've wasted a very valuable $1.20 piece of MDF. So it's more your time that we're worried about right here. And honestly, taking that time, oh, what's going on right there? Taking that time up front to make sure that you've got it right. I don't want to erase right there. I want to trim. Yes, thank you. Get that section out of there. so that it all comes together. Now, the other thing that you may want to do, depending on your construction technique, I like to do this, is I like to put a little hole in the middle of each of the nodes so that I can fit my spacers in there. And our thinnest spacers, the little bamboo skewers, when I measured them the other day, they were about 3.5 millimeters in diameter. So I'm going to come along here and I'm going to put a circle right there. And remember, that's diameter, so I hit a D, okay, and go 3.5. Or of course you could, figure out what the radius is and go ahead and put that in. We've already got our 13 millimeter nodes right down in here, so they're all good to go. I'll put some more circles in and then we'll talk about what I do next. I should say, once you've got one circle in there and you know it's the correct diameter, you can always just use the copy command. And tell it I want to copy that circle, use that center as your base point right there, and then bring it around. And while you're doing this, check to make sure that each of your nodes looks good and that you've trimmed it properly, because, oh my goodness, like I say, I know somebody for sure is going to miss one, and then they're going to be coming off the laser and they're going to be disappointed because they wanted to test their beautiful truss, but now they got to wait in line to get back on the laser. There we go. So 3.5 millimeter diameter circles on there everywhere. All right, so this is starting to look like a truss that we can analyze and we can calculate. We've got a few ways to do some more complex analysis on it. I'm going to talk about them in a moment. But before we do, let's prepare this one for the laser cutter. And what I'm going to do is I'm going to put this all into a group. And make sure you don't select any of the blue stuff on here, but if I come right down here, draw from the bottom corner going up and include everything right in there, that becomes a group. You could give it a name if you want, but that's okay. Now when I click on that, that all comes together like so. Now one way to check and make sure that everything's working out well is to do the hatch command. So hatch, and it asks you to pick an internal point. And I'm just going to pick an internal point right here. And you can see that went out and that filled the entire structure with a hatch. And that's useful to us because if I come in here and right click, why is this going slow right now? Oh, because it's trying to calculate hatches. So hit escape because I'm done. Come inside right here, highlight the hatch and highlight the hatch and go properties. And we should get the properties of the hatch, which is conveniently showing up on the wrong window for me so that you can't see it. There it comes over here. So on the properties for our hatch, under geometry, I've got the area showing as 9446 square millimeters. Okay, so that to get that, I went right click on the hatch and I got 9446 square millimeters. And I'm just going to write that down. Off to the side here, and we'll do a quick calculation with that in a moment. Once you've got that number, and once the hatch is showing you that everything's filled in nicely, you can get rid of the hatch, and you can use undo to undo that hatch. We certainly don't want to be cutting that hatch out on the laser. Okay, when you're getting ready for printing, you've got one of these on your sheet. You've grouped it together. So, of course, you can copy this. You can copy it and specify your base point. And this one's short enough that you can just put it right up there. In fact, this is a wee tiny truss. You may go taller than that. If you do, what you may find it useful to do is to rotate your truss 180 degrees and then move your truss so that it nests nicely together right in here. You could almost get 3 or 4 sections of this truss out of this design right in there. Okay, and while you're at it, you know, come in here and place your name here, and truss design demo number 1. Actually, this is truss design number 1 as far as this demo is concerned. Now, this should all be ready to go out to the laser and to be cut, and there should be instructions on the laser, so I'm just going to save this file right here, and I'm going to put that in my laser cut file, demo truss 2022A drawing, and I'm going to save that right over top. Excellent. You could take that to the laser and start cutting that out. You've probably got about 15 minutes of cutting right there. But let's use that to do a little bit more analysis before we go too far. And so the first analysis I'm going to show you is using the JHU, John Hopkins University Truss Analyzer. And I've got that open here in Firefox. And it looks something like this. To find it, you can just Google JHU, John Hopkins University Truss. And you will find the Truss Simulator from John Hopkins University pops up right here. And this is free to use. It's pretty nice. I'm still moping about the fact that Autodesk took Force Effect off the App Store, but anyway, they've done a whole bunch of other great things, and we're going to be talking about Fusion 360 later on. Now, there's a few things that you need to do to get this set up to do a reasonably good analysis of our trusses. First of all, you need to maximize the size of the window. And so we're going to change this up, and it can't go up to 600 that we want. So we're going to set it up to 62, which is about as wide as it can go in units. And we're going to set it up to 32, which is about as high as it can go in height. And you'll notice that grid disappears because the grid is just really tiny. Let's set that up to a grid of 5 by 5 and update that. Okay, there we go. So now you can see we're clicking around, and our mouse location is jumping from place to place on there. Working great. Now we want to make our window a little bit bigger, and this depends on the size of your screen. But if I set that to 1024, that gives me a lot more width on there to play around with and a lot more things to see. Now, you can see that I am snapping to a 5 by 5 grid, which is great for getting started because we know the locations of some of our nodes. So I want to come in here and I want to add some nodes, okay? And I'm going to start with my far left side node right there, and you'll see that's labeled as node 0. And then if I come down here, that one you can see was located at minus 30. Watch this location right up in here. That's at minus 30 comma minus 15. So if I come over here, there's minus 20. So I've come over 10, 20, 30, 40. Okay, that's where my force is going to be applied going downwards. And another 15 represents the 150 that it's coming over that way. Now, it is going to be 147 up from this node. So I'm just going to draw that top node in right there. And you can see that one showing that it is node 3. And here's node 3's location. Now, this one right here is mouse location 10 over and minus 15. And this one is 10 comma 0, so that's come up 15 or 150 millimeters. You can come down here and you can probably tweak this in. This is 10 comma 0. This should be able to come down a little bit because we wanted 147. That would be like minus 0.3. And there you can see we just lowered that down that tiny little bit, and it's gone off the grid. So the grid might be useful. You can set the grid down to smaller details if you want to snap to smaller amounts. So if you set it to 1 by 1, now you're going to snap to smaller amounts, and you can see in here I'm snapping 1, 2, 3, 4, 5 at a time. So that's kind of useful. Now, if I take a look at my AutoCAD drawing right here, I can figure out where some of my nodes are. And so come in here to AutoCAD, and here's one drawing that I did. And I wanted to enter this in here, so I used the dimension command, and I measured the horizontal and vertical differences from each one of these nodes so that I could get them in there precisely. So in this drawing right here, if I wanted to know how far over this node was right here, I can just go dimension, take my measurement from right there, bring it over here, and that's going to be 183 to right in there. Okay, that's all along the baseline, 183. Oh, I didn't want to rotate that. I just wanted the 183. So I'm going to come in here, and I'm going to come down here. So 183, that's going to be 18.3 over from here. So I could count that out. Or I could say, well, node 0 is over at minus 30. If I come over 18.3 from there, it's late at night, I'm using my calculator, minus 30, 18.3, going to give me negative 11.7. So I'll come in here and get this somewhere close. Negative 11, I'll put it right there. And then I'll just edit this right down here to say negative 11.7. And then I'll come over here and take my next reading off of AutoCAD. And anyway, I'll go through and measure some of these and enter them into there. And you can take vertical and horizontal measurements. Okay, so I took the dimensions off of AutoCAD, did a little bit of math, and entered them into this table right here. And you can actually go in there and edit them just like you would in a spreadsheet and control the X and Y locations of each of your nodes pretty easily. And then once you've got all your nodes in there, you can come in here and you can start adding members. And so we've got a member that comes from here to here, here to here, here to here, here to here. Okay, I did round off a little bit on some of these, so if this isn't coming in perfectly straight, you'll see why, and that is probably going to affect our analysis a little bit. If you forget what the truss looks like, just flip down here, and this one comes out to 3 nodes right here. And this one comes out to 3 nodes. Right here. Yeah, there's a little glitch in there, but we can tweak that in just a moment. Now, once you've got that all set up, you can click on Solve Once, and oh, I'm getting ahead of myself. We need to add some supports. So we've got a pin support down at this end. That node is pinned. We've got a horizontal roller at this end, and we have a force coming down right here. Click on the one and draw downwards if you can. Did we draw that just a little bit too low? I need to increase the size of my grid, maybe 33 lets me draw that force coming in right there. And I said my force that I estimated this is going to be able to hold is going to be pushing downwards with 192.5 newtons. And that's just off that chart. Wonder if I can make that a little bit taller. There we go. And so now we can see that force pushing down there with 192.5 newtons. And now I can hit on the Solve Once button. There's my 200 newtons that I calculated coming down there, my reaction force of 140, my reaction force of 52 down on this end, and slight differences right along here. This one's up a little bit high right here. So, but basically we can see our 150 newtons coming down along that side right there. And I think we calculated that was going to come out to 153. So given the little glitches in our geometry, that should be perfectly fine. Blue members are in tension, red are in compression. So we really need to be careful about those red members right up there. Now this has a really neat feature on it if you want to play around on here. You can click on the solve during move right here and then adjust your grid down to 0.1 by 0.1 so that you're moving things really fine. And you can come in here and you can click on node 12 and you can position it exactly where you want. And this lets you play around with your design just like you were able to do in West Point Bridge Designer. And you can say, where do I want to put this to play around with it? As you change this, okay, you'll see that the lengths and the forces get updated. So the forces get updated right along here, and your lengths of each member get updated right down here. And if you ever see a number that's less than 7 in this column, well, then that means member 7 goes from node 3 to node 12. Where is node 3 to node 12? Oh, right up here. That was moving that around. I made that just a little bit short. I'm going to have to come up here and drag it down this way. Because if it's less than 7 on the scale, (11 to 12) is getting too short. There is a number in there. There we go. That's exactly where it's supposed to be. 6.99. I'll live with that for drag and drop to the nearest decimal point. So you can play around with that in there. Make sure that none of your lengths are less than 7. Now you can actually use this to do all of your truss design and play with it just like you would with West Point Bridge Designer and get numbers in here. And if you know how strong your strongest member is at any given distance, you can take a look at that and say, hey, I've got a load of 200 in this member. That's from 7 to 6. There's 6 to 7 right there. It has a length of 7. You can look up in your data table and say how big should that member be, and you can use that as part of your design. So you can use an entirely different design path. These numbers right here, they made sense to me. I like sketching it out on paper first. Maybe you like to play around with it on here first. Now, the catch with this is that this is a very ephemeral file. It's going to evaporate. So when you've got a design that you like, okay, use your print screen command and take a screen capture of this section right here, okay, and capture that so you can see a picture of it all, and then roll up here a little bit and do a print screen. If you can get it all on one shot, that's fabulous, okay, but take a picture of all this. And you know what? You may as well capture this right down in here and give credit to John Hopkins University because they created a nice tool and they made it available free for you. And take a snapshot of that and save those two into your Word document or wherever. And now you've got this as reference that you can go back to later on, and you could use that to design your AutoCAD file. So that's one way to go about solving all that. That's perfectly fine. Do it that way. You don't have to do anything else. It's a neat tool if you want to come in and change things. So maybe you want to say, well, what happens if I change something in right here? So you can come in here and you can move and you can delete a single thing. So you can come in here and you can delete that member. And now if you try to get it to solve, it won't solve because that's no longer a truss. But if you put a member in that, add a member from there to there. Now this is back to being a truss again, and you can solve that. And you can see if you start getting some different numbers in here that work better for you. Okay, this is also going to change the mass of your truss. Now, I was talking about the mass of your truss, and we got a number out of AutoCAD, and that number I had written down on a sheet of paper right over here. was the truss that we had designed in AutoCAD and that we were going to go and cut out. Yeah, that one right there was when we used our hatch command, 9,446 square millimeters. Now we are going to make that 3 millimeters thick. So you can take that and multiply that by 3 millimeters, and 9446, enter 3 times, is 338 millimeters squared. Now, millimeters cubed. Millimeters cubed isn't that useful a number until you think about the fact that a cubic centimeter has 10 millimeters on this side, 10 millimeters on this side, and 10 millimeters on this side, and 10 times 10 times 10 equals 1,000. So this is actually equal to 28.338 cubic centimeters. And if the density of your MDF is, well, the same as water, then it's going to be 28.338 grams for that side of your truss. Okay, so two sides of the truss will be 56 grams. Add in a few grams for your spacers and some glue. You're probably looking at like a 65 gram total truss. Now, I just used a value of 1 for the density. MDF floats last time I checked, not very well, but it does float. So hopefully that density is less than 1. So you can get a measurement for the density of your MDF, and you can get a pretty good estimate of how much your truss is going to weigh just by taking a look at your AutoCAD diagram. All right, now stop right there. If your brain's tired, you're already confused, you don't need to go any further. But you're probably saying, Jason, you promised to show me how to get this into Fusion 360 and do some of that cool finite element analysis stuff that comes up with all the cool colors. And so I saved what I think might be the best for last. Let me get rid of. Okay, so you've got your AutoCAD drawing right here. Now you could do this drawing entirely in Fusion 360. Fusion 360 has a great CAD engine in it, and it does have some advantages, but I'm not teaching Fusion 360 in the class, and you're not going to learn Autodesk Inventor until next semester. So we're going with AutoCAD, which is part of our curriculum right now. If you're happy to jump into software and play around, go ahead and try it. It's pretty cool. Okay, and we are going to be using Fusion 360 in our circuit board design portion of your numeric control course later on, so it's worth downloading and installing Fusion 360. But we're also going to use it for designing some things for 3D printing. It's really amazing software. Anyway, so what we're going to do is we're going to take this entire shape right here, and we want to export that as a DXF file. And the quickest way to do that, I think, is to do a copy clip, okay? And you'll notice I like to type in my commands. You can also right-click on it and do a copy that way. And then from my copy clip, I will come in here and I'll create a new drawing. And just a blank drawing. And you can come in here and you can go to the clipboard and you can paste. And there is our truss right in there. And I really don't care too much where I put it. Take a good look at it. Everything still looks good. You always want to be double checking that before you go to laser cut it. But and now I'm just going to take this, and it's the only thing in there. I'm going to save this as a drawing. And when I save it as a drawing, I'm going to save it as a DXF format. DXF was developed as AutoCAD's drawing exchange format, and that's designed to allow you to take it from one program to another. So 2018 DXF will work, AutoCAD 2000 DXF will work. It really doesn't matter, just make sure it's a DXF and save it in here. And this I was working on the name Demo Truss 2022A.dxf. Okay, now I'm going to start up Fusion 360. And it's opening up on my other screen, so I'll wait for it to open and then I'll come back. Okay, so you will need to log in with your Autodesk account to make Fusion 360 work. And when it comes up, you'll have a list of files over on this side, list of projects. So on this side of the screen, you should see your name in here because you're logged in and you want to create a new project. I've already created one called Truss Analysis, and this is where I'll be saving my design. Look at this, I've done this before. Uh, so let's come in here and take a look at a few other things. Up here, you've got a view window and this view cube, I think it's called, and that allows you to rotate it around and look at your drawing from different points of view. You can also do that using your mouse. I have a funky little 3D mouse right here, and if you like 3D CAD, oh my goodness, this is a connection, 3D connection mouse, and it is the coolest thing for working in 3 dimensions on your computer. And you'll see me using it quite a bit for zooming and panning around. Anyway, the way most of our parametric solid modeling works is by creating a sketch. So the first thing we're going to do is we're going to create a sketch, and we're going to pick a plane to put it on. There's 3 planes right here, and let's choose a vertical plane right in there. Doesn't really matter. Comes up right in here. I'm scrolling in and out with my center mouse button. And now I am going to import, okay, a drawing, and I go to Insert and Insert DXF. And I've got my sketch selected, and I go Select DXF file. It looks on my hard drive, and I say I want Demo Truss 2022A.dxf. And there is that truss. And make sure that you bring it in as millimeters. Okay, probably a good thing to make sure your account is set up for handling millimeters. Don't worry about the fact that it's upside down. Okay, that's all you need to do to get your truss into Fusion 360. We're going to finish that sketch, and now you're going to do an extrude. And you're going to extrude this profile by 3 millimeters, because that's the thickness. Now, in a 2D point of view, you won't see too much, but when I flip it around, where did it all go over there? Come back here. It's going about some different axis. There we go. Now, that's what one side of my truss is going to look like. Now what I'm going to do is I'm going to create a copy of that. You do that by using the move copy command. Okay, and it says, what do I want to move? I want to move bodies. Well, I want to move this body here. Pick something that gives you a nice pointy flat axis in 1 or 2 directions. Okay, and then click on the Create Copy button. And then how far do you want to move it apart? You have to be a minimum of 40 millimeters apart. So move it 50, 45, whatever you want. You can type in a number right there to control that. Okay, now if you want to come back and change that later on, all of your commands are being recorded on the timeline down here. So if you double click on that at some point and you wanted to move it in a different amount, you can. Okay, now we have to connect these together. Okay, and we're going to connect them together at their nodes. And to do that, I'm going to create another sketch on this face right here. Oh yeah, it whips it around and flips it upside down for me. And so what I'm going to do is I am just going to hit the P button for project and select the outline. right like so, and say OK, and that's all I have to do. I'm going to finish that sketch right there, flip that around right over here so I can see that that way again. And now I am going to extrude, but this time what I'm going to extrude is all of the little holes where I'm going to put my barbecue skewers or my dowel or whatever I'm putting on there. Make sure you get them all. I mean, you can always come back and do this again if you forget one of them, but your analysis will be a lot more useful if you get them all this time around. And there we go. We've got them all on there. In fact, don't do this bottom one. I'll show you why we don't do that bottom one in just a moment. Now it wants to know how far do you want to extrude them. And rather than doing a distance, you should be able to say to object, and then just come in and pick this plane right over there. And we are going to join them together. And now I've got barbecue skewers and nice thick dowels coming across right there. And that's starting to look like a truss. Now, I said don't do this one just yet because we need a tiny little flat space pointing downwards because that's where we're going to apply our load. Okay, so we're going to create one more sketch right in here on this plane. Okay, right at that center node where we haven't joined it. We want it to be going down. It's flipped us upside down right on here for some reason. Don't worry too much about that. Do the project command again. Select that outline right there. Say OK. And now just draw a line, very tiny little line from right there to right there. Make sure it intersects with the circle. Okay, perfect. And that it is perfectly horizontal. Finish that sketch. And now we're just going to do another extrude. But this time when we do the extrude, you can see we're extruding that flat little bit so that it comes distance. We don't want distance, we want to come to an object right over here, and we're joining. And now we've got a tiny flat little surface right down there. That's going to make it easier for us to apply a vertical force to that when we look at doing the simulation later on. Okay, we're almost ready to go and start doing the magic. But there is our truss. Looks beautiful. There, I'm overlapping it and making it look less beautiful. Now, we do want to come in here. We've got one body in our structure, and if I right click on that, then I can change the physical material of this. And the library pops up right in here. Now, I could make this out of metal, and I could run my analysis for a solder truss or an aluminum truss, but we're going to come into the wood settings right down in here, and it has parameters for medium density fiberboard. And so I'm going to grab MDF and just drag it right over here on top of body one. And you'll notice a slight color change in there, and it says medium density fiberboard is in this design, and we'll just say OK. Now, this truss is ready for analysis. And in fact, we can do a quick inspection on it right here. And we should be able to come in here and, just trying to remember which one gets me the total mass is whether I click on the properties down here, because now it should know the density of medium density fiberboard, keeping in mind that medium density fiberboard and hardboard are different materials. Okay, let me just, I think it's inspect and center of mass analysis. One selected, I just had to select it. There we go. There's a center of mass sitting right in the middle. If I had to balance this, it would be right there. And somewhere in there, I can now get the um, I can get the total mass of it. It's in there somewhere. I'm going to move on to doing the analysis. Um, that may have been the incorrect route. Maybe it's just plain old measure. Measure body 1, select body, body 1, and anyway, there's a way to do it. I'm just mind blanking on it right now. Let's get over to the fun part. Design. Okay, come on in here. We're going to come into simulation where we get the pretty pictures. Okay, and we are going to start by doing a structural buckling simulation. This is an amazingly complex calculation, and when I was a student at BCIT, this would have been PhD level work. We are now going to knock it off in 30 minutes or less. And so let's create a study and come in here. We can rotate it around. Don't know why mine is being so fussy. I'm rotating about the wrong point in here. There's a button down here to zoom all. There we go, fit. I'm orbiting the wrong point. It's constrained orbit, that might be. There we go. Okay, get it nice and square on your screen right on here. Now we need to apply some parameters to this. It's just like in any other analysis program that you do, you've got to apply some structural constraints. And we are going to apply a structural constraint, and we are going to apply a pinned constraint, okay, to our dowel at the back. Okay, that's actually going to be a metal rod when we test it for real, and that's going to be resting on our loading apparatus, and it won't be able to move radially, so it can't move up, down, sideways, it can't move axially side to side, but it is able to rotate. So it's a pin joint right there. And then on our other constraint, we're going to do a structural constraint. And this one, we're going to do a frictionless constraint. And we're going to apply it to this node right here. Sorry, not a frictionless, a fixed constraint. We are fixing that in place. And if you look at this right here, we don't want it moving in the z-axis because the z is up and down. So the z is turned on. We don't want it moving in the y-axis because that's side to side. But it's okay if it moves forward or backward in the x-axis. So I turn off that constraint. Okay, that's not perfect because there's still rotation and that involved in there, but it's not too bad. Now, down at the bottom right here, you'll remember we left a little bit of a flat surface, and I said that was where we were going to apply the load. And so we're going to put a structural load in right here. And it's going to be a force, and it says, what are we applying that force to? And make sure you get the whole surface right on there, not just the edge. And we want a magnitude of minus, we said 192 newtons. Now, keep in mind that 192 newtons was for just one side of the truss. So really, we should be applying 192, enter 2 times, 384 newtons coming down right there. So we're hoping that it'll be able to hold 384 newtons. What we're actually going to do is we're going to enter 1. I know that seems weird. We're going to enter 1, and this is going to tell us how many more times than 1 newton it's going to be able to hold. Okay, so it says 1 newton working that way. Don't worry that it's pointing in the wrong direction because it analyzes it both in the push and the pull when you do a structural buckling analysis. Now, because it analyzes it in the push and the pull, we need to get some more data out of there. But before we do that, let's come over here to solve and let's just do a pre-check. And you should see this little message pop up saying that it's got all the information. It's got a continuous structure, it's got a force, and it's got constraints. So the body's not going to start accelerating anywhere. Okay, so we've got that all in place. When we come over here to solve, we want to come in here and go to solve, and we need to tell it that we want many different failure modes. We don't do that there just yet. We're going to go to solve in just a moment. We want to come into here and take a look at load case at attributes, structural buckling analysis settings. There we go. Number of modes. So right click where it says structural buckling and go to settings. And we want about 50 different modes of failure because we need to have at least one that shows it being pulled down this way. Now you can go to solve and click solve. And this is going to send it out onto the clouds. Now, if you were a commercial customer of Autodesk, they would solve this for you on their servers for 18 cloud credits, which you would buy from them, which is about $18. Since you're a student and they would like you to get hooked on their software and learn just how wonderful it is, they do that for you for free. So it doesn't matter if you got a slow computer, you've got Autodesk's computing power at your ready. So shut up, Jason, and solve one study. Oh, you do need to save it, right? Demo Truss 2022A. And there we go. It's gone off to the cloud to be solved. I'll pause here for a moment and wait for the results to come back. Okay, so we're back and it tells us the analysis is complete and we'll click on close. Now, this doesn't look like how it's actually going to fail, okay? Because as you can see, the buckling is occurring in the bottom, and we know the bottom is going to be in tension. So let's just come along here, and these are all positive modes of failure. Let's find our first one that looks like might be, whoa. Looks like this one's suggesting that we're going to have some structural buckling right in here. Now, the results are pretty exaggerated, but it's suggesting to me that this is the weak point in our structure right in here, and that if we're worried about buckling in here, we need to reinforce this section. Or what it also, well, we also have buckling occurring right in there. It's very rare that that would occur in both of them. And what this is telling me, it says this is occurring at 117 times the 1 Newton load that I entered. So this would suggest failure at 117 Newtons rather than the much higher value that we calculated. Let's take a look at some of the other buckling failures that we might see. Again, in this structure, it's going to be the negative ones. This is the same type of failure, but popping out to the other side. Yeah, more buckling right up through there. It definitely seems to be focusing on this section right in here as the point most likely to fail. Now, one of the neat things about its analysis is that it's doing a much more complex analysis than just the truss analysis can allow, because it's actually taking into account that these sections right here aren't pinned, that they're actually fixed. Now it's also showing a little bit of warp right in here because we did say those materials would be MDF. We might not have the right materials in there, and we might get different results if we used a thicker cross section in there to make that more rigid, so those are less likely to pop out to the side. What other failure modes do we have right in here? We've got quite a few. Generally, the first one that you want to see is the first one that triggers failure in the direction that matches with what you're looking at, and we're looking at 117 right there. So little less than we expected, and if I had to focus an area right now on places to stiffen up, it would be right along the top right here, and it's got me thinking that that might not be the best design, and I might need more reinforcement coming right through along in here. Well, I'll have to make that truss, and let's see if it holds up, because the proof is in the actual testing, and you have to match your real model to check that you're getting meaningful results in the real world. A model is great when you're competing on the computer, but when you want something to work in the real world, your model better match the real world for it to be valuable. One last test that we can do, now this has told us that we're looking at 117 newtons of failure, is that we can also come in here and take this model right here, and this only takes a look at the compressive failures and the structural buckling, and it's telling us that we're going to expect it to fail somewhere around 117. We should check to make sure that it's good in tension as well. So what you can do is you can clone your study. Okay, and here's another study taking place right down here. Don't worry about the fact that it's upside down. You can flip it back up if you want, but really, so long as the force is there and the supports are where they are, you should be good. And what we're going to do is we're going to change this, and we're going to change our settings on the study. Actually, sorry, we want to change this type of study, settings, properties. Okay, I don't want it to be structural buckling anymore. I want it to be solve. Got to be settings, general study to struct. Oh, here we go. Under study type, change it to static stress. Okay, click OK on there. And under your load case, take your load and find force 1 on there, and go to properties on force 1, and instead of 1 Newton, okay, we want to change that to a value in the Z of 117 newtons. Oh, 1. Oh, okay, we want to edit that. Loads, structural loads. We'll just get rid of this and we'll put a new one in. Loads, structural loads on this force, on this face, I should say, right there. And we want minus 117 because we want it pointing that way. There we go. And that was what it predicted our buckling would occur at. And now we want to take a look and see, will all of our members also be okay when they're loaded in tension with that load? They probably will be, but hey, it costs us nothing to solve this, so let's solve it. Goes quite a bit quicker for this one. It's a simpler calculation, but I'll pause anyway. While I'm waiting for this to solve, I thought I should mention that if you're having problems getting this installed on your computer, if you go to fusion.online.autodesk.com, Autodesk does actually have a web-based version of Fusion 360, and you can launch Fusion 360 just by signing in. Well, I guess I've got to update my password. Guess I've got to remember my password. And you can actually run it in a web browser, and so you should be able to run this from basically anything that can run a modern web browser. I haven't tried doing it off my iPad or anything like that, but maybe. Um, kind of handy if you get into a battle with IT services at your school about what can and can't be installed on school servers. I don't know if all of the options are available in the web version, so I haven't tried it out with the structural buckling and um, and the finite element analysis yet, but it probably works fine. Anyway, it'll boot up in your web browser and you can run it from there. Looks like we're still waiting for this to finish, so I'll just wait for a moment too. Okay, the results are back, and oh, where is it telling us that we have a safety factor below 1? So that's suggesting, it's showing us the buckled section right in here. Oh, that moved in the wrong direction. That's as if it was being pushed up, so I'm not surprised that it failed. I must have got my measurements entered incorrectly because that should not be sitting high, that should be sitting low. So I'm going to have to change that force and try that again. Let's change that to a positive 117. Unlike the structural buckling that solves for both push and pull, this one only solves in one direction, so you've got to get the direction right. While we're waiting for the results to come in from our truss test, this is the web version of Fusion 360, and this is a project that I did some time ago, and it seems to be in here and working, and the rendering isn't quite as good. The speed seems to be a little bit slower. Down here you can change up your display settings so that you can have just plain old shaded, not shaded with hidden edges. And I think I should be able to come in here, and if I adjust that joint right there, I should be able to use that to, now let's try rotating a joint. I've got a whole bunch of joints in here that should be able to control each other. Anyway, Fusion 360 does work in the web version. All right, looks like we've got some results in here. Let's close that. And that's also pushed it upwards. So something weird's happening in right here. That should be pulling downwards. And so obviously I've set something up with garbage because my results look like garbage. But this should be giving us a case where this is bending downwards and we see what's happening in there. It's not happening right now. It's getting late. We're late into the video. If you're at this point, you can play around with this anyway. And you did get the structural buckling results right in here. And those are the key ones that suggest this is going to fail at 117 newtons. I'm going to cut this out and try it in the lab and see, does it fail at 117 newtons or not? Thank you for putting up with this. I used to think that Fidel Castro spoke for a long time, but he didn't have the option of having students put him up to 175% speed on YouTube. So have a good evening. I hope that helps you get off to a start with analyzing your trusses.